Hi, this video is on section 10.2, and we're comparing the means of two distributions. I'm going to share the notes again so you can follow with them. All right, so section 10.2 is inference on two independent sample population means. That would be like a mu1 and a mu2, assuming that the standard deviations are equal. Okay, so there are a lot of different procedures for comparing the mu1 and mu2, depending on what's the structure in the in each of the distributions, distribution 1 and distribution 2. So it turns out that often when we're comparing means from one distribution to another distribution, that the distributions are already similar. And it turns out that often we're in a situation where we can assume that the standard deviations are equal. And that's the work that's presented in section 10.2. In section 10.3, it gets generalized to where the standard deviations are not equal. So that's important too, but honestly, most of the time when I'm comparing means, when I'm really seriously thinking that two populations are close enough so that their means are equal, what's going on is that the distributions themselves have similarity in terms of their spread as well. So the 10.2 becomes actually, I might say, the statistical technique that I use the most in my work, all right, or very similar techniques. So we're going to cover 10.2 in this class. We will not be doing all the other variations. We won't be going into 10.3. We won't be compared. So we'll only be doing two independent sample means when the standard deviation is equal. The other comparisons are very similar in how you use them. In particular, if after this class you go to a class where you're going to be working in a software system to do comparisons, it becomes it's a pretty straightforward extension of what we're doing here. So our goal is to teach you well inference of two independent sample population means where the standard deviation is assumed equal. And have that be kind of like something that's strong for you and clear. And so then in the future, if you need to generalize, I do believe you'll have a pretty straightforward time doing that. Okay, so when is it valid to assume that the standard deviations are equal? When is it valid to use the procedure that I'm about ready to present to you? So it's valid to assume that the standard deviations are equal if we look at the larger one divided by the smaller one, and that ratio is less than 2. So when we pull up our standard deviations, we look at the larger sample standard deviation divided by the smaller sample standard deviation. And if that ratio was less than 2, then it's reasonable to assume that the underlying standard deviations are equal, and we move forward with the procedure that I'm about to lay out. So if we're in this situation, then we need to form a test statistic, and here it is, this T statistic. We need to form a test statistic so that we can, for the hypothesis test, and it has a couple of parts to it. So the first thing is that since we've assumed that the standard deviations are equal, we are going to pool S1, the sample standard deviation from sample 1, and S2, the sample standard deviation from sample 2. And we're going to pool them together to find one estimate, one pooled standard deviation, SP. Okay, and this is then going to be estimate the standard deviation sigma, right? Because we assume the sigmas are equal. So now we only have one sigma to estimate. So we want to put the information from both samples into that estimator. So SP is equal to N1 minus 1 times S1 squared plus N2 minus 1 times S2 squared divided by N1 plus N2 minus 2. Now, I know this looks like a complicated formula, but I have to tell you, I don't usually have to take, I almost never have to take points off of the final exam for this formula, that people really do get comfortable in using it. And I'm even going to give you some internal checks to see if you're on target with your SP. So let me just run through, and I just wanted to say that even though the formulas seem a little complicated, I think that we should be able to have a lot of success in them. So Z, my standard, we know that Z is equal to, from the previous section, that this X bar 1 minus X bar 2 minus mu 1 minus mu 2 over this standard deviation, that this is a standard normal. And what we're going to do is we're going to estimate the sigmas with the S sub P, and we end up with a T statistic. Okay, so in a similar manner that we went from Z to T in chapter 9, we're going from Z to T here in chapter 10. And it has this form here. X bar 1 minus X bar 2 minus mu 1 minus mu 2 over SP times the square root 1 over N1 plus 1 over N2. I will show you how to use it. The degrees of freedom on this T statistic are N1 plus N2 minus 2. Okay, so what do we need in terms of assumptions? We're not going to go through it like you can see here. This is a 6-step hypothesis testing recipe. I just want to go through the assumptions, and then I'll jump over and give you an overview of how to do this work. Okay, so first is we need, of course, that the samples are simple random samples, that they're independent, that each of the X bars is either yielded from a normal parent population or a large sample. So we do need that normality of X bar that either comes from underlying normality of parent or large sample. And then in this procedure, we assume that sigma 1 equals sigma 2, that the two populations have the same equal standard deviations. Okay, so what's new here? So we have, in terms of assumptions, really like we're in chapter 9, we had the first pile, the first 3, and then that is normality of the parent or large sample. And now we have this added equal population standard deviations for the 2. So the assumptions are similar with one additional one. Okay, and we're going to go through a process where we set up a null and alternative, and then the steps are exactly the same, except the calculation here, it gets a little different, right? So the first step is going to be null and alternative. The second step is going to be an explicit statement of your significance level, alpha equals whatever alpha equals. And then in step C3, we calculate the test statistic, which does have a different form, okay? But in step 4 and 5 and 6, it's exactly the same. So really this test has a lot of similarities to the test that we learned in chapter 9 for one population mean. I want to just move through and show you how this works out for this example here. So back to the driving distances and the vehicle miles traveled. This was our summary statistics table, our summary table. And you'll note that I have now identified the Midwest. I put a subscript 1 here, X bar 1, then is the sample mean from the Midwest population, and X bar 2 is the sample standard deviation from the South population. Okay, and we're asked at the 5% significance level, does there appear to be a difference in this year's mean VMT for Midwestern and Southern households? So here we have a keyword. Does there appear to be a difference? So when we get down here to set up the null and alternative, my alternative hypothesis is going to be is going to come from that keyword. Okay, so first I just want to jump in, like, we don't have to calculate SP before we start the hypothesis test, but just to make sure that students do that, on your exams often, I will ask you for SP before I ask you to jump into the 6-step hypothesis test to remind you that you need to calculate it, right? So just trying to give you a little help with that. So in the notes here, I'm going to calculate SP before I jump in to calculate the hypothesis test. But again, you certainly can include this calculation down here in step 3. So let's look at the calculation. So SP has this long formula here, but what it is for the first distribution, it's N1 minus 1, so that's 15 minus 1 is 14. And then I have to square, oh, here we are, sorry. So then I have 15 minus 1, square of S1, plus 14 minus 1, the square of S2, divided by 15 plus 14 minus 2. Okay, so again, we're going to take it easy and go a little slow with the calculations. I myself never put them all into a calculator and hit it in one line because I know that I wouldn't get it right. So I always break it down. Also gives me opportunity to check and to check with you guys to see where our agreement and disagreement falls. So just following through, first step here, we square the standard deviations and then multiply and continue through. So notice here that my final answer is 4.24. I need to look at that value, and I want to compare it to these values, okay? That is my pooled standard deviation, 4.24, must be between S1 and S2, okay? So if you that's your internal check. If I'm pooling my standard deviations together, I have to have a value that's somewhere between the two of them, because really to say pooled standard deviation means it's a combined standard deviation. So it takes information from both of the samples and it necessarily must be between those two. So if it's not, then it's an arithmetic issue. So go back, find your arithmetic problem. Okay, so we're all set. We set up the null and alternative hypothesis, and in this case, we have discussed already, the keyword is difference that we're trying to flag, so the alternative hypothesis is not equal. The significance level is given here in the statement of the problem, and now we have to calculate our test statistic, okay? So taking some time here, substituting in mu1, x bar 1 minus x bar 2, minus mu1 minus mu2. Guys, just to simplify this, I think in all of the work we're doing, x bar 1 minus x bar 2 in the null hypothesis is 0. That is to say, this is a little more complicated than it really needs to be. And I just simplified it a little bit. So for our situation, we are always working in the and with the null hypothesis that mu1 equals mu2, so that this is the simplified t statistic. And I just brought up our formula card, so I just want to take a look at what the formulas look like for chapter 10 before we move a little bit further in on that hypothesis test. So scrolling down to chapter 10. Okay, there's that test statistic, all right? Pooled t-test statistic for the null hypothesis, mu1 equals mu2. We need independent samples, normal populations or large sample sizes, and equal population standard deviations. So it clarifies exactly what the situation is where these statistics are valid, okay? And so we have here the t statistic, and that's our sample, our pooled standard deviation, and that's the degrees of freedom. Okay. So coming back to the notes, we see our test statistic subbing in x bar 1 minus x bar 2 over SP times the square root of 1 over n1 plus 1 over n2. And that gives me numerator minus 1.46 and denominator 1.57. And calculating then, dividing here, we get minus 0.93. Okay. Next step would be to determine the rejection, non-rejection region. So I just brought the problem over to the whiteboard. And we need now to determine the rejection, non-rejection regions. Step 4. Okay. So step 1 tells us it's two-tail. We're going to be doing the critical value approach, because even though an approach wasn't offered or wasn't told in the problem statement, because this is a t-test, we're going to be using the critical values from the t-table. And again, when we do t-tests, we either are going to use the critical value approach, but if we want to do a p-value approach, we're going to have to be on some kind of more detailed software system other than just working with our tables. So for pen and paper or pencil and paper and the whiteboard, we're always on t-test going to do critical value approach. Okay, so over here, this is a T. Right, so that's a T. I just want to be able to mark your degrees of freedom here. And so the degrees of freedom are 15 plus 14, N1 plus N2 minus 2. So the degrees of freedom are 27. And we need alpha over 2.05 divided by 2.025 in each tail. Okay, so we need to go to the t-table for 27 degrees of freedom and find the 0.025 critical value. So let's go ahead and get our t-tables up. 27 degrees of freedom. Please follow along and catch me, because if I have any errors, I'm going to want to know about it. 0.025 gives me 2.052 as my critical value. Okay, so now I want to label the rejection, non-rejection regions. So the middle is the do not reject, the null hypothesis region, and then the tails indicate the rejection regions. Okay, so let's just look at what we have in step 3. We got a test statistic of 0.93. Now, I am going to circle it in red and bring it down and put it on the on this graph down here. But even before I put it on the graph, I want to remember this, right? So I want to think about it. Is this a large value? Is it in the tails, right? Is it big enough that our intuition tells us we're going to reject the null hypothesis? Or is this value sort of more moderate? And we see that it's less than 1. So whenever it's less than 1, it's quite moderate, right? So it's in the middle of the distribution. It's going to be in the do not reject region. So we're going to go ahead and pop that in there. Okay, and so our decision is to do not reject. All right, so let's kind of put that in for step 5. Do not, you guys see that? Maybe not too clearly, huh? Okay, so I'll move step 5 over here. Do not reject. null hypothesis. And then step 6 is going to be a statement of our conclusion. Okay, let's go for it. It's going to seem very similar, guys. It has the same structure. At the 5% significance level, the data does not, because we did not reject, right? So the data does not provide evidence or provide sufficient evidence that, and over here, I'm going to put a statement of the alternative hypothesis that the mean VMT for Midwestern households is equal to, or is not equal to, it's a statement of the alternative hypothesis, or I can say differs, right? Differs from the mean of the Southern households. Okay. So very similar, right? The interpretation at the alpha significance level, the data either does or does not provide sufficient evidence that the alternative hypothesis is true. All right. Our 6-step hypothesis testing procedure. Okay, so I'm going to break the video here, and we'll be back in part 2 to look at the calculation of confidence intervals.